light imprints. Really, really crazy, kind of new, fairly new area of science. Pretty badass. Okie dokie. So you think about it like, those things with the little metal rods where you push your face in, it leaves the imprint. Light does the same exact thing. Is that cool? I think that's so really cool. Higher density, lower velocity, higher index of refraction. And now we got Uncle Snelly's law. So let's do an easy breezy example. So woozy. Now before we do that, let's talk about this critical angle. This is so annoying, and they test it so frequently. The critical angle. So here you are underwater, and if you're underwater and you shine a light up, well, interestingly enough, there's a particular angle that you shine the light, and none of the light escapes because your angle of refraction is 90 degrees. And of course, we're humans, we categorize everything, we give it a name. So this is called your angle critical. Your critical angle, what's critical about it? I have no idea. How does this apply to any kind of science? I've never heard it applied to science other than it's tested frequently. So the critical angle is the angle of incidence. What have you used it for, Ian? The angle of incidence that results when you were playing in the bathtub. What the hell did you use it for, dude? Hey, tell me what it was used for. Nonlinear optics and plasmonics. Oh, that's what I was thinking. You go with your wild self. Ian, you sound like a guy I want to party with. Nonlinear optics and plasmonics. That was going to be my guess. The angle of incidence that results in a 90-degree angle of refraction. The angle of incidence that results in a 90-degree angle of refraction. So this tells us right away that the critical angle, what has to be true about the different substances? If that's a critical angle, what are you doing? You're bending how? You're bending away. You're bending away. Towards, no, dude, look. How can you say that's towards? How can you say that? This would be the same. Okay, if this were our angle, this would be the same density. If you go that way, it's towards. We're going this way. We're bending away from the normal. So when you bend away from the normal, this has to be a less dense medium. So you can only have a critical angle when you go to a less dense medium. Everybody understand that? It makes sense. So you can only have a critical angle when you bend away from the normal because you have to have a 90 degree. The minimal angle that results in a 90-degree angle of refraction is called the critical angle. So what would that look like? Well, if you have n1 sine theta 1 equals n2 sine theta 2, right? And we're trying to get this to be 90 degrees. The sine of 90 is what? 1. So should you memorize this equation? No. I mean, you should understand it, right? So any angle more than the critical angle will result in total internal reflection. Yes, Miss Elena, that is correct. That's where we're going with this. So the critical angle, you might even say it's equal to what? N2 over N1. Everybody see it? All I do is not magic. Sine of theta. I need sine of 90 to be 1. That's my critical angle. So just as Miss Elena just pointed out, if I increase this angle, googy, then sure as hell no light escapes. When no light escapes, we call it total internal reflection. Total internal reflection when no light escapes. Total internal reflection. So long story short, critical angle of incidence that results in 90-degree angle of refraction, or you might say the angle of incidence that gives you the first total internal reflection. Let's do it. All right, folks, let's start off with an easy one. So let's say N1 is 3, N2 is 2. Calculate my critical angle, go. N1 is 1, N1 is 3, this is 2. Calculate my critical angle, please. Shine a light, won't you shine a light? Oh my God, Scott Roberts, I'm expected to be able to bracket sines and cosines? Yes. First of all, can there be a critical angle? Well, last I checked, and I want you to memorize this cold, that index refraction is proportional to the density. Clear? So the density went down, so sure as hell we can bend away. Away, away. So sine theta equals what? 2 over 3, which is 0.67. Last I checked, sine of 30, 0.5. Sine of, are we there yet? Not yet. Sine of 45, root 2 on 2. Should you know root 2 is 1.4? Yes, you should. Root 2 on 2, 0.7. Ooh, very close to 45. Sine of 30, we're what, Bubba's bracketing. Sine of 30 is 0.5. I'd say it's a hell of a lot closer to 45, like what, 42 degrees? Sounds good to me. Any question? Should you be able to bracket that? Yeah. So when the angle of incidence is 42 degrees, you will get what angle? Oh, no. Okay, so let's go back. Miss Elena, where the hell are you paying attention? Sine of the incident angle. So it's 3 times sine of incidence times sine of what, folks? For the critical angle, sine of what? Sine of 90 times 2. Sine of 90 is 1, so 1 times 2. Miss Elena, I know you know better than this. Sine of theta potato is here, and now we get a 2/3. Got it? That's for you. Sine of 2/3, well, that's a 0.67. Sine of theta, you're welcome, is 0.67. And there we go. So our angle of incidence is 42 degrees. Our angle of refraction was 90. Moving on. Let's try it again. That was so much fun. Okay, if I shine the light, won't you shine? I'm going to shine a light with 30 degrees. And this is n equal 1, and this is n equal 3. Calculate your angle of incidence. Go. Calculate your angle of incidence, please. Calculate your angle of incidence, please. You can do better. Calculate your angle of incidence. N2 is 3. Calculate your angle of incidence. Yeah, I know, that's terrifying. Folks, would they do this? Yeah, they would. You guys, they've done this before, and you're like, what? Wait, what? Oh my God. Guys, it's just 60 degrees. That's it. That's your angle of incidence. But I need you to do something more difficult for me. Calculate your angle of reflection. Calculate your angle of reflection in this problem. Reflection is 60 degrees, is 60 degrees, is 60 degrees, is 60 degrees. Now, let's calculate our critical angle. Go for it. Ian says, no, I won't do it. And Danny's speaking to me in some strange tongue saying, you cannot. You cannot. Good. You cannot. I agree, you cannot. Because this is more dense. So what happens when it's more dense? It's going to bend toward the normal. So you'll never, ever get to 90 degrees. Got it? Now, my lovelies, let us, but how? Reflection, 60 degrees. Because the angle of incidence is 60. You always reflect off a surface, period. Always. There's always a reflection, period. You get a reflection, and this is the angle of refraction. This is the angle it bends. Bend it like it's hot. So now calculate my angle of refraction. I know they sound the same. Refraction. Got it? So that right there is the angle of reflection. My diction. And that right there is the angle of incidence. And that right there is how much you refracted or bent. All right. Calculate my angle of refraction, please. Well, certainly it has to be what, folks? Right away. Quicker. It better be what? It better be the morning after. It better be what? And by 30, you mean 60. It better be less than 60. Yeah. All right, my little Snelly fans. 1 times sine of 60 equals 3 times sine of theta potato. I like it. Sine of 60, last I checked, is root 3 on 2. Yes. And then we're going to divide it by 3. Makes sense to me. So what do we get? 1.7 over 6. Well, 2/6 is what? 2/6 is 0.3, right? 1/6 is what? 0.17? Get it? Should you know that? What are we doing, Bubbas? What are we doing, Bubbas? Bracketing? What's the probability that 1.7 over 6 is between 0.17 and 0.3? 100. 100. Got it? 100. I don't know. Maybe like what? Closer to what, for sure? It's closer to... Everybody see what I'm doing here, I hope. It's not that complicated. Why gotta make it so complicated? So, what are we doing with this newfound knowledge? So now we got to say what? Well, we know. What do we know? Because I feel like we know something. Maybe I'm wrong, but I feel like we know something. We know that. I mean, we didn't even need to go this far. That's my point that I'm trying to get to, guys. Got it? So again, 1/6, 0.17, 0.3, 2/6. This is really close to 2, so who knows? Like 0.27, 0.28, or something like that, whatever. So now we get the sine of theta potata is 0.28. Well, what do you know? I know sine of 30 is what? 0.5. Are we surprised it's less than 45 degrees? No. Why would we? We shouldn't be surprised at all. And then we know that the sine of 0 is what? My little bracketing wonders. The sine of 0 is, I believe, 0. Damn, that looks like it's pretty much in between, doesn't it? So if that's in between, what does that mean to you? Everybody know what it means to you. If that's in between, what it means is, how about the sine of like what? What do you want? Give me some. Give me some. Sine of 15 degrees. Yeah, why not? 15, sine of 30, who knows? Yeah, sine of 15, sine of 17, somewhere around there. It's about 15 degrees, right? It's a little close to 0.5, so maybe we'll say, I don't know, 17 degrees, 20 degrees. That's fine. So theta is about 20 degrees, guys. Get it? I dig it. I dig it. Any questions? Should be getting the hang of this. I know I am. Okie dokie. So we understand the critical angle a lot better. Critical angle is the minimal angle that results in total internal reflection. The critical angle is the angle of incidence that results in a 90-degree angle of refraction. Love it. Okie dokie. Let's talk about some mirrors and lenses. So we got some stuff to memorize for mirrors and lenses. A lens is double-sided. A mirror is single-sided. This lens, so these are lenses. Correct. These are lenses, and these are mirrors. Lens comes in, boom. What is that lens doing to the light? I believe that's called converging. What is that mirror doing to the light? I believe that's called converging. So you need to be comfortable knowing what these mirrors and lenses look like. Got it? Converging mirrors and lenses. So happy we have this time together. Okay. Divergers, what do they do? Well, I'm going to show you what they do. Divergers take light and diverge it. That makes sense. Diverger, bounces all like Superman there. So divergers diverge the lights. So if we diverge the lights, now here's where it gets a little bit interesting. I don't know if it's really that interesting, somewhat interesting. And what I find interesting is there's a definition of what a real image is. And I find out that you guys really don't get it. And a real image is where the light really is. So a real image is where the light really is. So what does that mean? Well, I'm going to tell you what that means. What that means is this. If you see an image here, there's light really there. If you see an image here, there's light really here. So we're going to call that for real. So here's where the light goes through a lens. So if you see an image here, it's for real. If you see this image here, it's for real. But if you see images where there's no light, it is your mind screwing with you. Got it? So if you see images where there's no light, it is indeed virtual. So a virtual image is where there is no light. A real image is where there really is light. Ooh, I feel like I get that now. Very nice, very nice. Okay, I think I can handle that. So now, the next thing I need you to be comfortable with is my nice little handy dandy chart. And the chart works as such. You ready for this? Because I think you're going to be very excited about it. The chart goes F, I, O, and M. F, I, O, and M. You got to memorize this chart, guys. You get every freaking mirror and lens question passage. I don't know, about every third MCAT has a passage. So you're talking like 6 or 7 questions on this. Positive and negative. Ready? C, D, R, V. Everything's alphabetical. A, N, E, I. Anytime you have a focal point that's positive, it comes from a converging mirror lens. Anytime you have a diverging mirror lens, by convention, the focal point is negative. Anytime you calculate I and it's positive, it's for real. And that would mean it's on the opposite side of light for lenses and on the same side of light for mirrors. Anytime you calculate I and it's negative, it's virtual. Now, you don't read this straight down, and I'll tell you why. Because we need to know that M, which is magnification, are you bigger or smaller, is minus I over O. And here's what I'm going to tell you. O is positive when? Does anybody know when O is positive? Always. O is negative, never, ever. Ever, ever. O is negative, never, ever. M is erect. Erect means upright or it's inverted. Got it? So when M is positive, it's erect, and M is negative, it's inverted. So check it out. If M is minus I over O and O is always positive, that means that M and I are always opposite. Always. This I would like you to be very comfortable with. And if that's true, that would mean that all real images, I is positive, M is negative, all real images are inverted. Conversely, all virtual images are erect. I feel like I get that now. So all virtual images are erect. Love it. Good. Okie doke. Now, let us take a look at this beautiful equation. 1 over F equals 1 over O plus 1 over I. Wonderful heavenly equation that's going to get us about 8 gazillion answers on this test. So what happens is 1 over F, 1 over I. Well, here we go. This is always interesting. We know this is a positive term, period. Where does the FIOM stand for? Focal point, image. So this is the focal point. This is the image. This is the object. And this is magnification. Magnification. Are you bigger or smaller? Are you bigger or smaller, folks, is pretty straightforward. If the object is greater than the image, then you're smaller. If the object is less than the image, get it? If the object is greater than the image, you're smaller. If the image is greater than the object, you're bigger. You see what the focal point is. Where the light focuses. Where the light points. Yeah, right here. Focal point. Boom. Focal point. Okay. No, not necessarily. Nothing to do with it. No. The sign of M just tells you whether you're erect or inverted. It has nothing to do with you're bigger or smaller. Nothing at all. So if you understand the sign of M is just whether you're erect and inverted. And the sign of I has nothing to do with the size either. So like -6 and 6 are the same size. the sign of I. So if you have an I of 6 or negative 6, which one's bigger? They're the same size. So it's kind of like an absolute value thing. You understand? So when I is 6 or I is minus 6, the same size, this would just be what kind of image? What would that be? Today be good. What kind of image? Well, no, that's not right at all. What the hell, dude? No, wait a second. Guys, holy shit. Yeah, real. What? Oh, no, no, stop. Why is everybody giving me these bad answers? Okay, look. No, I know. Yeah, there you go. Guys, okay, look. If I is minus 6, you go over to the handy dandy little chart, which apparently is not so handy. Negative I means it's virtual. And M is the opposite in sign. When M is positive, it's what? Erect. But if there's another image that you got was 6, that would mean it's what? I is positive, it's what? For real? And if I is positive, we know M is negative, it's inverted. Do we understand? So which one's bigger though? The I that's 6 or the I that's minus 6? Which one's bigger? Same. Okay, hopefully that's a little bit better. We're gonna do lots of this. I know it's a colorful slide, but man, you really got to know this slide. I would like you to really know the slide. Can you really know the slide? Yeah, you really. So everybody know the slide. I'll be very happy. I am very happy. Let's try it again. So F positive negative, I positive negative. It wasn't, Raquel. There was just a lot of other people saying it. Object is never negative in sign. Yeah, that's why it says never. Okay, so let's roll. Always pick the numbers 2 and 3, and it will reward you very well. So let's say I have this. Let's do this lens. And let's say I take, now here's the words. They'll say the object is placed within the focal point of what kind of lens? It's also called a cave because that looks like a cave. Got it? Don't forget, that's a cave, concave. And then this looks like a vex. So that's convex. Got it? Convex, it bubbles out. Concave, it bubbles in. So this is a concave lens. And what do we know about a concave lens right away? F has got to be what? F has got to be what? Concave lens is diverging. F has to be what? F has to be negative. So who's 2, who's 3? Well, who's closer to the lens, the center of the lens? Who's closer to the center of the lens, the object or the focal point? Object. Object is 2. That makes the focal point what? -3. -3, because it's a diverger. -3. -3. Yes. Okay. So the question goes like this. They'll show an object and they'll say, hey, here's an object. No, they'll just say, they're going to do it in a word. They like word problems better. And they'll say, because they can make you got to figure out multiple things. So they'll say an object is placed within the focal point of a diverging lens or of a concave lens. And they're going to say, describe the image. Describe the image. Well, first things first. We have 1 over -3 equals 1 over 2 plus 1 over I. I sure as hell has to be a positive or negative number. I's got to be negative, because if this is positive, wait, why did I assign O to be positive? Anybody know? Why did I assign O? Because it's always positive. I love it. And here we go. If this is 3, 6, and this is -2, 6, I know this is complicated math. So what does I end up being? This is always terrifying. What do you get an I to be? Well, you got to invert it, dude. That's 1 over I. Like I said, complicated math. Oh, boy. Move the -3, 6 over, invert it, and we get -6/5. Any question about that? We good? Because I feel like we solved that. So I is -6/5. Clear? So, no, the -3 was not given. We set it at -3. So if I is negative, we know it's virtual. And if I is negative, we know that M is positive because they're opposite in sign, so it's erect. And last but not least, is 6/5 a bigger number than 2? No. So it has to be what? reduced. Everybody feeling it? So we got a little reduced erect virtual image. Is it on the left or on the right? Where is it on the left? Where is it? 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 Close. Well, closer to the lens doesn't make sense. Between what? Between the lens and the object makes total sense. So you got this little reduced image. Hello, I'm the image. To the right of O. How about between O and the lens? Can we say that on the left-hand side? How about, here's my little image. And it's looking very erect for that little boy right there. It's virtual because the light really is here. So it's virtual. That is our image. Okie dokie. So now let's try it again because that was invigorating. Let's do a mirror. Well, let's do this mirror. I got this beautiful mirror here, and I'm going to take my object and put it outside my focal point. All right, folks, calculate, or tell me about the image produced. Tell me about the image produced when you take an object and put it outside the focal point for a concave mirror. Sure. Tell me about the image produced when you take an object and put it outside the focal point of a concave mirror. Well, you should kind of know, back to our handy dandy little chart that apparently didn't copy down. What does a concave mirror do? Concave mirror does what? It's right here. Here I'm right here. Converges. Okay, who's 2, who's 3? Who's 2, who's 3? F is 2, O is 3. Now, is F positive or negative 2? Positive, positive, positive. Why is it positive? Why is it positive? Because the converger. So now we just do our handy dandy 1 over 2 plus 1 over 3. So we get 1 over 2 equals 1 over 3 plus 1 over I. 3, 6 equals 2, 6. Well, I'm seeing I as what? I'm seeing I as 6. Does everybody see that? So I is 6. 1 over 2 equals 1 over 3 plus 1 over I. I is 6. So if I is 6, well, is that bigger or smaller than 2? I feel like 6 is bigger, so it's magnified. You think 6 is smaller than 2? Kenneth, we gotta have a little talk here. It's magnified. I is positive.
Lindsay, look at this video of Murphy.
It's for real. And M is negative, so it's for inverted. Good job. A lot of y'all put that.
Isn't that funny?
Goodbye. Hello, puppy.
Now, what happens next? No, Dan, that's ridiculous. It's so easy. I'll talk about it afterwards. Where is it?
Murphy's in here because he thinks there's
Where?
someone
We already
in here.
did magnified. Where is it?
He's not in here.
Where is it going?
Bye.
And where you gonna be? It's for real, and it's gonna be way the hell out here. And here this guy is. It's gonna be this big pumpkin image in front of mirror behind. What the hell does that mean? In front of mirror behind O. Yeah, to the left of O. Very good. So there's your image. Is it for real? How do we know? Because that's a 2, that's a 3. The positive means it's real, and we did reals already. Remember, reals were on the left, vaguely, basal vagal. Good. There's our image. All right, we'll do one more, and then we got to move on. Let's do totally different thing. Let's do this. Here we go. And we got a focal point here, object here. Did I do this one already? I don't think I did this one. No, I didn't. Good. Oh, good. No, I didn't. All right, cool. All right, describe my image. Describe my image. Describe my image. Do, 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 do. Mm-hmm. Mm-hmm. Describe my image. Okie dokie, who's two, who's three? I do not love this. This is so much fun. Who's two, who's three? I feel like you're two. I feel like you're three. Now, what kind of lens is this? Converging or diverging? Diverger, diverger. Divergings have F's that are what? Negative. Oh, so we get 1 over minus 2. So the rules are simple. Set 2 and 3. Now, folks, don't use 2 and 3 if they give you 7 and 12. If they give you the numbers, use their damn numbers. Scott Roberts, this doesn't work. Why did you use 2 and 3? You told me to, but it says 7 and 11. Well, oh, okay. Little independent thought, my little mitochondria. Powerhouse of the cell. There's J.J. Watt. What? Set 2 and 3, and then assign positive or negative to F, based on whether it's diverging or converging. Okay, so we get 1 over minus 2, and then you use your formula. 1 over F equals 1 over O plus 1 over I. Now, listen, you can solve it, but you don't really need to, because what you need to realize is if this is a positive number, this has to be negative. Got it? Because the whole thing is negative. So we know right away I is negative, and therefore M is positive. We know that in 2 seconds. And we also know that this term must be bigger than this term, because the negatives win, right? It's a negative. So if this term is bigger than this term, I has to be smaller than O, because I, it's 1 over, right? It's 1 over. So this term, so I has to be smaller than 3. It's smaller than O. So if this term is bigger than this term, then I has to be smaller. Everybody feel that? Or you can just solve it if you want, but I'd rather you not. All right, how does it make it? I is negative, it's what? For virtual? Erect. And I is smaller than O, it's reduced. That's what I get. You guys get the same? Let's see. Virtual record, let's see. Good. Couple. Yeah, virtual. Reduce, looks good. Okay, good. All right, cool. Any questions? You should be an expert in this now. Where is it? Light really ends up here. Where does light end up? Here. So anything over here is for real. Or red, apparently. You understand? So we got a virtual one, so where is it? On the left, on the right. On the left, now we actually have to calculate to find out where it is, right? So we get minus 3, 6. This is 2, 6. We get minus 6 fifths. Didn't we just do this? Pretty much. So it's over here. No, on the right is real. It's on the left, and you get minus 6 fifths, I hope. So it'll be right here. And it would be virtual, erect, and reduced. Virtual, erect, reduced. Okay, now listen, I'm going to do this pie in the sky, but listen. So will they do multiple lenses? Yeah, they can, but they'll then do multiple lenses. They're going to do it like this. They're going to give you everything to calculate where this image is, right? So you'll get the image over here. And let's say my image is here. If I get the image here, then this image becomes the object for the next thing in the line. You understand? So like they'll give you a bunch of stuff, you calculate your image, you find out. In this case, is my image real or virtual for the lens? Real or virtual? It's real. So they'll calculate this, you'll get this real image, so I would be positive, yada, yada, yada. And then they'll give you the distance between these, and they'll say, okay, now they'll give you, so you calculated your I, and now this distance, what is D minus I now? Let's see if we're paying attention at all. What is D minus I? Anybody paying attention? It's O. It's O. Very good. Somebody's paying attention. That makes me happy. So now it's O. So that's my new O, and then I use my O, and they'll give us a focal point in the mirror, and then yada yada. Everybody understand? So you can have multiple lenses and mirrors. It's just you got to keep track of what you're doing. And don't forget, if this thing ended up inverted, this thing might make it go upright. You understand? So just because you get an inverted from this mirror, it might be upright because it re-inverted the inverted one. Woo! Everybody got that? I don't want to do one of these because it's kind of rare, but I do need you to be comfortable that if they do it. Got it? Good. Happy times. Okay, I think we kind of get that now. Mirrors, lenses, looks pretty good. Oh, by the way, if you think about it, all diverging mirrors and lenses, all diverging mirrors and lenses. Look what this says now. 1 over F equals 1 over O plus 1 over I. All diverging mirrors and lenses. What does I have to be? Well, if 1 over F is negative, 1 over O is positive, 1 over I has to be what? It has to be negative. And we know if I is negative, M is what? Positive. And we know one more thing. Which term is bigger? The 1 over O term or the 1 over I term? If you had a positive and negative, the 1 over I term has to be bigger. That means I has to be what? Smaller. Kind of weird, right? So anything diverging is virtual, erect, and reduced. Kind of interesting. I don't think I memorized it. I think I understand how to manipulate this. Got it? My little manipulators. Good. Erect, and it's going to be, the image is smaller, so it's reduced. Nice. Okie dokie. Well, let's talk about your eyeball and what happens in eyeballs. So for an eyeball, we're supposed to focus the light right onto the retina. Does that always happen? Hell no, especially after you go to medical school. If you're all not wearing glasses after medical school, all that reading you're going to do, especially everything's on the computer now, you'll all need glasses after medical school. It is ridiculous how many people need glasses after medical school. So this is what's supposed to happen. It's about 2 centimeters in a normal eye. If you drill the hole through your lens of your eye, you get about 2 centimeters before you hit the retina. So if this is 2 centimeters, then what happens is we have conditions that you need to understand. One of those conditions, the light, because the lens gets a little pudgy and starts to get dehydrated, the light focuses early. And that's going to be something called myopia. Myopia. So if this is the retina, we focus the light before the retina, we call it myopia. Myopia, my means near. You are nearsighted. So you can see near. So myopia, you're nearsighted. You can see near. And then there's something, and of course, how we're going to correct this myopia, we're going to give you a diverging or a concave lens. And what that does is the concave lens will take the light and it'll pop it out a little bit. And when it pops it out a little bit, now it can come back and focus on the retina. Got it? I like it. I like it. And then you have something called hyperopia. And hyperopia doesn't really allow you to focus the light. Because if you did, you can't like send light through your retina. But if you could, then this hyperopia would focus the light beyond the retina. Got it? Beyond the retina, this hyperopia. And this is far. Hyper means far. Hyperopia. So hyperopia, you can see far-sighted. Hyper, far-sighted. So how do we fix hyperopia? Well, we're going to give you a what? Your lens will be a converger. And then what are we going to do to fix it? We're going to converge the light a little bit. When we converge the light a little bit, we fix you. We fix you. So how do you fix hyperopia? This is a classic question, guys. You fix it with a converging lens, better known as a convex lens. How do you fix myopia? You fix it with a concave lens, better known as a diverging lens. Nice, nice. All right. That's our eyeballs. More to come with eyeballs later, but we got to move on to some Doppler, baby. I love Doppler. So for Doppler, there's an observer. For Doppler, there's something called an observer, and the observer is going to observe. And interestingly enough, if you have somebody running at you, and let's say they have this speaker that goes all over the place, and they're running at you at 50. And then you had somebody running away from you, equidistant, so we'll put the observer dead center. Let me try and move our observer. Excuse me, observer, would you mind moving? I would love to. And I have this observer here, and let's say I had somebody closer who was running away. Is that legal? Yeah. And they're making the same decibels. So they have both the same decibels, the same noise level, same decibels. But he's running away at 70. Which does the observer hear louder? Top or bottom? Hello, I'm an observer, yes I am. Yikes. Yikes. Wow. That's interesting. Oh boy. Intriguingly enough, I've got about 14 answers. Only one of which is right. Okay. Whoa. Okay, loudness has nothing to do with Doppler. Loudness is simply distance. Intensity, amplitude, that has to do with loudness. And that goes what? That's related to distance, 1 over d squared. You should understand this. Got it? So loudness has to do with how close you are. If you're closer, it's louder and it's quadratic. So who's closer, the 70 or the 50? 70's closer. So if the 70's closer, the observer hears it louder. Are we clear on that? I agree. B, shark, do. So, without a doubt, because this is closer, it's louder. There's nothing to do with Doppler. Doppler has to do with frequency. So if I asked you which one has a higher frequency, that's a different thing. So which emitted frequency is higher? Which emitted frequency is higher? Same. Emitted. Emitted is what I'm emitting. If I'm emitting the same decibel, it's the same. It's the same. But that's not what I'm going to observe. I'm not observing. The emitted is what I'm emitting. That's the same. Got it? So now the observed frequency will be greater, even though the emitted frequency is the same, it'll be greater because you're adding energy to the wave. Here you're kind of elongating it and pulling it away. So long story short, and this is a very, very important concept, and that's that as you're going towards, the frequency will increase for the observed. The observed frequency will increase, and because the observed energy increases. Observed energy increases, observed frequency, and therefore the wavelength goes down, right? Because they're opposite each other. What does this guy do? As he's going away, he's pulling this wave, he's elongating it. So here, the wavelength is getting longer, and obviously, if the wavelength's getting longer, I know I wrote density, if the wavelength's getting longer, I was kind of marveling at my lambda up there. I don't know if I've ever done a better lambda. It's the little things in life, guys. Higher wavelength means lower frequency. Long story short, when your relative velocity is going towards, the frequency increases. When your relative velocity is going away, the frequency decreases. And that is a very important concept. So Doppler is obeyed for very important waves. Does anybody know what kind of waves? What is it? All waves. I love it. Like what kind of waves? Sound waves? Sure. Light waves? Sure. Water waves? Sure. Anything. All waves. Doppler's obeyed for all waves. Is that weird? I don't know. It is what it is. So here you are. It's the weekend. You've been hanging out doing your physics because, you know, that's how you guys roll on the weekend, which is probably not far from the truth these days. And what do you do on the weekend? You push your hair up, you put your cape on, and you whip out your telescope. Come on. I know it's you. And what happened? Oh, lo and behold, you saw a quasar. And your quasar was, wait for it, green. And you call up NASA, you're like, NASA, it's a green quasar. And they're like, no such thing. All quasars are, let's go with, I don't know, blue. So if all quasars are blue and you see a green one, is that quasar coming toward or going away? If I could hold your hand. Bruce Willis, really? No one? Really? Armageddon, best movie ever. Is the quasar going toward or away? Well, my Roy G. Biv fans, Roy G. Biv, really no one? Oh God, I hate this red shifted shit. That's so annoying. I'll tell you why it's annoying in a minute. Roy G. Biv. Oh my God, Kat, you would love it. You're gonna cry. You're gonna go hug your daddy after you see it. It's such a good movie. So, the quasar, I should have told you, is green. No one has seen Armageddon. What a great movie. What a horrible movie to watch now. Don't worry, Bruce Willis saves the universe. So I see it as green, but we know it's actually blue. So is this higher or lower energy going this way, going to the left? I hope you know the spectrum of light. The spectrum of light, UV, is higher energy. UV than X-rays than what? Gamma. Did you know this? Yeah. Next to R is IR. Did you know that? Then microwaves and then radio and TV. These are little wimpy waves. Got it? Very low energy. So going this way, going to the right is higher energy, which means higher frequency, which means lower wavelength. So let's see what you have to understand that you better damn well know the spectrum of light. So it's actually blue, but we observe it as green. So we see it with lower energy, which means lower frequency, means it's going toward or away. Away, away, away down south in Dixie. Got it? Away is correct. Again, blue was the actual color. I had to give that. And you called NASA, they said, oh, all quasars are blue. So, no, you don't have to know quasars are blue. They're actually a nice magenta. Green is a lower energy. Got it? Good. So here's why, getting back to, somebody asked earlier about this red and blue shift. That's annoying. Because what if you have violet and you have a blue shift? If you see something violet and it's a blue shift, what does that mean? If you observe something violet and it's a blue shift, what did that mean? It's going toward or away. Away, away, away. Blue is lower energy, guys. Lower energy, lower frequency. But if you're green and you observe blue, then it would be going towards you. Do we understand this? So let's do another one. All right, lo and behold, you witnessed a parsec. Got it? The amount of time light travels in a year. You witnessed a parsec. And you, my lovelies, saw a yellow parsec. Everybody knows that parsecs are actually red. So if they're actually red, is this parsec going toward or away? It's coming toward us. It's time to call Bruno. It's coming toward us. Yellow means higher frequency. Higher frequency means the thing's coming toward us. Get it? Love it. I think we're getting there. Okay. Formula for Doppler. Frequency observed equals frequency. Actually, got to memorize this formula, guys. V plus, minus, minus, plus, top is towards. VD gets around. VD and VS. Plus, minus, minus, plus, and use the top sign when you're going toward. Got it? Maybe. So here we go. I'm going to ask you to calculate the frequency observed to the frequency actual in the following scenario. I've got a source traveling at 20, and then I got a detector runaway traveling at 30. What is your relative velocity, folks? It's all relative, Einstein. What's your relative velocity? What's your relative velocity, folks? 10, 10 away, 10, 10 away, 10, 10 away is perfect. If your relative velocity is 10 away, because you go 20, you go another 30. If your relative velocity is 10 away, which it is, right? Every second, these guys are going to be 10 whatever, 10 meters per second, 10 whatever apart. If your relative velocity is 10 away, then the frequency that this detector detects should be more or less than the actual frequency. Frequency should be less because it's going away. There's a relative velocity at 10 away. So let's see how that works. How is it 10 away? If you do 20 and you do 30, right? I'm going to be 10 further from you. So you went 20 to catch up to me, but I went another 30. So we're going to be 10 away every second goes. When we put them right next to each other, if you go to 30, you go to 20, we're always going to be another 10 away. Every second, we're going to be 10 more away from each other. Okay, frequency observed equals over frequency actual equals. Well, my V is whatever the speed is. What's the speed of radio waves? I forget. Anybody know the speed of radio waves? Speed of radio? I'm on a Mexican radio. A radio wave. That's what? 3? No, Kenneth. Radio is light, dude. I'm sorry. Radio is 3 times 10 to the 8th. It's light. Sound. Radio emits sound, but radio receives radio waves, which are light. Is that annoying? Yeah, they like to get you on that. They did a whole passage, and in the passage, they gave you the frequency of sound, and it was like 340 meters per second. And they're like, here's 340. We'll give it, they give you big letters. They'll be like, look, the velocity of sound is 340 meters per second in this medium. And then the first question's like, okay, if I give you the frequency of this, calculate the wavelength of it, of a radio wave. Got it? And they didn't give you 3 times 10 to the 8th. Everybody feeling that? That's kind of douchey. I bet they did it more than once. Long story short, radio is light. Know it, work it, own it, live it. Okay, back to work. So let's say this is indeed sound. So if this is sound, we have 340 and 340. Now, detector, I said, was doing 30. Source is doing 20. Now, plus, minus, minus, plus, top is towards. I'm going to use the top sign when this detector's coming towards. I'm going to use the bottom. Plus, minus, minus, plus, top one is towards. And this is away. So is that detector coming toward or away? Is that detector? It's no detector's going away from the source. So that's going to be a what? Plus or minus? Minus. Ever see it? And now, is the source going toward or away? Source going toward. Is that the top sign? Yes, it is. The top sign is positive or negative. On the bottom, not the top now. That's top is towards. So we're going to get a negative 20. I like it. Are you surprised this number is bigger than 1? You shouldn't be. Why not? Because the frequency observed is greater than frequency actual. Get it? I like it. Told you, man. Told you. Let's do another one. All right, here we go. Let's say you're doing 30 and you're doing 50. So what is this? A source, this detector? What's our net? What is our relative velocity, Einstein's? Relative velocity. Quicker. What is it? 20 what? 20 what? No, 20 towards, man. This guy goes 50, but he goes another 30. So every second, there'll be 20 closer. This is 20 towards. So should that detector detect a higher or lower frequency? Higher or lower? Higher frequency. Everybody understand? I don't know why I keep writing that. A higher frequency. Get it? Good. Okay, let's do it. So we have frequency observed equals factual, F actual, times 340, 340. You should know about the speed of sound. Plus, minus, minus, plus, top is towards. Here's the 50. Here's the 30. Detector's on top. DS, it's alphabetical. Help me remember it. I don't know. I could lump you. All right, what do I do about this now? Well, the detector's on top. Is that detector going towards or away? Towards, towards, towards. Last I checked. Plus, minus, minus, plus, top is towards. Plus, minus, minus, plus, top is towards. Plus. The source is going away. What do you want to use, minus or plus? Plus, 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 away, away is the plus. Top is towards. Plus, minus, minus, plus, top is towards. You can't ever screw this up. So we get what, 390 over 370. Are we surprised that frequency observed, frequency actual is a little different? No, we shouldn't be surprised at all. I like it. You guys are so good with this. I'm so excited. Okay, that's pretty good for Doppler, I think. Don't forget, Doppler's not about loudness. Doppler's about my little freaks. So here's one of, sure, Miss Allie. Here's one of the interesting ones. One of the interesting ones is the harmonics. I think harmonics have to be the complete wicked stepchild of all of physics. This is easily, this is in specific gravity, which is a really simple concept. Harmonics is never taught. Just never taught. So let's learn harmonics, at least what you need to know, okay? Okay, harmonics. The first thing you have to realize is harmonics is just an observation of what a wave does. So somebody can say, hey, I want you to repeat this experiment. Run it in the third harmonic, run it in the second harmonic, whatever the case may be. So let's take a look at that. So there are three types of pipes. This is closed at both ends. This is open at both ends. And this is a test tube. A test tube, they're going to say a test tube because a test tube is a pipe closed at one end. They like to say test tube because it gets confused because you're like, is it a tube? Does that mean it's open at both ends? Well, no, a test tube is what? Test tube is open at one end. Then they'll say a closed test tube and that'll be closed at both ends. If you understand that? Yeah. Okay. Now, here's the first thing you're going to learn. You're going to learn about waves. The first thing you're going to learn about waves is wherever there's a flat end, you have to have a node. And a node is a point of zero displacement. So node equals zero displacement. And then anywhere there's an open end, you're going to have what's called an antinode. And we're going to have maximum displacement there. Okay? So far, so good. So here I have to start at a node and I have to end a node. That's just the way the sound is it's gonna set up like that. It's gonna do that. For the open end, I'm gonna start with what? A node and end at what? An antinode. So now when you calculate and you do this, each one of these waves are what's called in resonance. In resonance means you're doing what you're supposed to do. So if I showed you a wave like this, is that wave supposed to do that? No, and it doesn't. So you would say that wave is not in resonance. Got it? So, I mean, it's kind of stupid, really, right? It's like, why wouldn't you just say it's not, that didn't happen? They don't call it that. They just say it's not in resonance because everybody's got to have their own terminology. Everybody understand that? Okay, now, every time you do what you're supposed to do, it's another harmonic. So in other words, this wave only resonated once. That's why this is the first harmonic. This wave started an antinode and is supposed to end at an antinode. Well, there was a null antinode. That's why this is the first harmonic. This wave started at a node and was supposed to end at an antinode, and that's why that's the first harmonic. So I need you to understand how to draw the first harmonic because they'll say which line depicts the first harmonic. and you're supposed to be able to understand what it looks like. It's basically the longest wavelength that can fit in the pipe. You should understand. Oh, and then this is lovely. The first harmonic, this is exciting. Has about 52 names. The first harmonic is the principal harmonic. The first harmonic is the primary. The first harmonic is the fundamental. There's a few others, but I mean, just look for anything that says first. Got it? First, primary, principal, fundamental. That's pretty good. They all mean the first harmonic. And that's when what's called your N is your harmonic equals 1. Not index or a fraction. Let it go. That was so a while ago. Okay. So now that we are such good experts on this, look. Here's a pipe. What am I supposed to have on the left? Node or antinode? Node. What am I supposed to have on the right? Node. So now look what happened with this wave. This wave resonated here. So if I took that point out right there and I stretched it all the way to the end of the pipe, that would be the first harmonic. If I took this here, that would be the second harmonic. If I put this here and stretched it, that'd be third. If I took this here, it'd be fourth. So this is a picture of the fifth harmonic. Fifth harmonic, like what? Havana, like Cabela? No, she left the fifth harmonic. Come on, man. Everybody knows that. Come on. So anyway, come on, man. The first harmonic, if I took this point right here and stretched it all the way out, that'd be the first. If I took the second, I'd go here. So this is a picture of first harmonic. No, fifth harmonic. Everybody understand? All right, let's try it again. Let's do open at both ends. So if I took this, oh man, and I did this, I have to start an antinode. What do I have to end up with? What do I have to end up with? I have to end up with a what? Today we get antinode. So I did that. I resonated once. I resonated twice. I resonated 3 times. This is a picture of the what? Third harmonic. So they're going to straight up draw these things and say, what harmonic is this? Yeah, they're going to do that. Got it? Now, getting back to the first harmonic for a minute. In the first harmonic, how many pipes would it take to get one full wavelength? It would take 2 because this is a half of a wavelength. So it would take 2. Got it? That's why I could say this. This pipe L has a half a wavelength in it. And when I solve for wavelength, I get 2L. And for the first harmonic, it's N, 2L over N. So when I plug in a 1, I say wavelength 2L. So the formula when you have a half a wavelength in the first harmonic is 2L. Same thing here. Look at the first harmonic in this picture. The first harmonic, I started an antinode and I got to end an antinode. That's a picture of the first harmonic. How many wavelengths are in this pipe? This pipe L has how many wavelengths? It's not, no. Alex, if that was one full wavelength, your wave would look like this. It'd be a sexy looking wave, but that's not right. You see what I'm saying? It's not a quarter. No. Okay, look. So y'all are screwing this up. That's a quarter of a wave. That's a quarter of a wave. And then another quarter and another quarter. Get the idea? So that's a half a wavelength. So this pipe L has a half a wavelength. Does everybody see that? I need you to be very comfortable. That's sure as hell not one full wave, unless your wave is a woozy, which it's not. Got it? So, will ever not have half a wave? Yeah, of course it will. Of course it will. Sure. Look at this. How many wavelengths in this pipe here? So long story short, wavelength equals 2L over N when you're closed at both ends or when you're open at both ends. You should know that. So how many waves are in my pipe in the bottom? In the bottom right here, how many waves are in my pipe? How many wavelengths? 1. And then what? Half. You understand? That's 1.5 waves. Got it? 1.5 waves. You might even say it's what? This is 1 and then a half. So that's what? 3 halves. If that's 3 halves, so this pipe L has 3 halves wavelength in it, then you get wavelength equals 3L. 2L over 3. Oh, 2L over N. We just proved that's the third harmonic. Well, you should have known that because it resonated once, it resonated twice, it resonated 3 times. That's why it's a third harmonic. See it? See it? Okay, now listen. What part of a wave is this up here up top? What part of a wave is that? It's a quarter of a wave. It's a quarter of a wave. Good, 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 good. So can you say that this pipe L has a quarter of a wave in it? Quarter of a wavelength? Sure. Can you say that 4 wavelength equals 4L? It would take me 4 pipes to get 1 full wavelength. Everybody see it? I'm up, down, up, down. 4L over N. So when it's open at one end, the equation is 4L over N. Okay, now watch. And this is really important, so make sure we're paying attention to this. So what am I supposed to do at the end of my pipe? For this open and end, what am I supposed to do at the end of the pipe? I'm supposed to have an antinode. I'm supposed to have an antinode. So how many times did this wave resonate in this pipe? Twice. Once here? No, Kenneth, look. Twice. If I pulled this right out here and I pulled it out there, this would be the first harmonic. So that's the first time I resonated. This is the second time I resonated. Everybody see that? This wave resonated twice. It's supposed to hit an antinode. It did it once. It did it twice. Got it? Okay, now, if this pipe L has how many wavelengths in it? How many wavelengths are in this pipe? Here's a quarter. Here's a half. Here's a quarter. Here's a half. And then here's a what? This pipe L has 3/4 wavelengths in it. You might say that wavelength equals 4L over 3. Ooh. So that means that our N is 3. So here's a statement you need to be very comfortable with. When you have it open at only one end, there are no even harmonics. The numbers don't work out. That's all there is to it. So there are no even harmonics, period. If you calculated an even harmonic, it didn't happen. The wave wasn't in resonance. It did not happen. Got it? It did not happen. So let's try it again. I think this makes sense. Take a picture. Okay. I'm ready to have some real fun. Okay, this wave resonated how many times? How many times did this resonate into the pipe? Beautiful. 5 times. You can't have a half resonate. That doesn't make any sense. You're supposed to hit an antinode. 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 So, are there any even harmonics? No. So, if I took this point right here and pulled it all the way out, that would be the first harmonic. If I put this point here, this would be the third harmonic. If I took this point right here, it would be the 5th harmonic. Havana. No. It's now only the 4th harmonic, I think. If I took this point here, it would be the 7th. So this is a picture of the what harmonic? This is the ninth harmonic. Even though it only resonated 5 times, there are no even harmonics in open-ended tubes. There are no even harmonics in open-ended tubes. So let's try this again. What if I said, how many waves are in this pipe? What would you tell me? Would you be like, I'm not telling you. I hope you tell me. How many waves are in this pipe? One. There's one. There's two. There's two. 2 1/4. 2 1/4, which happens to be what? 2 1/4, 2 times 4 is what? 9/4. So this pipe has 9/4 wavelengths in it. But if I solve for L, what do I get? I get wavelength. I know it's real complicated, multiplied by the reciprocal. Wavelength equals 4L over 9. And I thought when it's open at one end, the general harmonic equation is 4L over N. Oh, we just proved the ninth harmonic. So what's the entire point of this? The point of this is for reproducibility. So when you want to reproduce a certain wave in a pipe, we know how to do it now. And now I feel more confident that you guys know how to do this. Maybe. I don't know. Maybe. Okay. So let's try this. Can a 3/2 meter wave, so a wave with a wavelength of 3/2 meters, can it resonate in a 20-meter long pipe? You ever wonder that? Can a 3/2 meter wavelength wave resonate in a 20-meter long pipe? You ever wonder that? Me too. Well, what are we going to do? Well, if it's open at both ends or closed at both ends, we can use 2L over N equals what? 2L over N equals wavelength. Wavelength equals 2L over N, right? And we know that 2 times 20 over what? We can switch and say N equals 2L over wavelength. So 2 times 20 over 3/2. Everybody feeling it? So what are we going to do? Invert and multiply, and we get what? We get 2 times 20 times 2 over 3. And what do we need this number to be? My little holy wonders. Needs to be whole. Is it a whole number? No. 4 times 20 is 80, isn't it? So 80/3 is not a whole number, right? If you add up, did you guys know if you add up the digits, it's divisible by 3, then it's divisible by 3, right? So it's 4, 3, 1, 7, 8. Is that divisible by 3? 15, 16, 16, 7 is 23. The answer is no. Everybody understand? If you add up the numbers and they're not divisible by 3, then it's not divisible by 3. Hopefully everybody knew that. But in any case, so long story short, it cannot resonate in open or closed, but you didn't check the other one, did you? So let's check it. Can it resonate 4L over N equals wavelength? I can switch these two and say N equals 4L over wavelength, right? So my length is 4 times 2 is 80 over the wavelength, which is what? 3/2. Multiplied by 2/3. Is 160 divisible by 3? Well, 7's not, and therefore it's not. So let's try it again. Can a wave that has a wavelength 3/2 meter resonate in a 20-meter long pipe? The answer is what? No. 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 For the for the 4L over N, we have to get an odd answer. If it's not odd, then it can't resonate. Everybody understand? If it's not odd, if it's not odd. Good. Okay, now, if I told you very nicely that one of these bad boys is the first harmonic. So this is a picture of the first three harmonics. Which is which? By the way, you should really know that amplitude is irrelevant to wavelength and frequency and velocity. Velocity equals frequency times wavelength. They all depend on each other. Got it? That's what there was one other thing I want to tell you guys. Listen, let's go back to mirrors and lenses for a second, because for some reason you guys usually tend to screw this up. When I increase my object distance, what happens to my focal point? When I increase my object distance, what happens to my focal point? Up or down, folks? Up or down? Yeah, no. Focal point is inherent in the mirror or lens. You have to buy it. If you want to change the focal point, go buy a new mirror or lens. You understand that? So focal point, it's like the battery. When you have a battery, if you have a 9-volt battery, how do I change this battery from 9 volts? You unplug it and you put a new battery in. If I add more resistors, what happens to the voltage of this battery? Do you understand? If I add more resistors, what happens to the voltage of this battery? Nothing. Can't. It's a 9-volt battery. It's a thing. You understand? So, Danny, not really, Danny. I always teach it, so it's not just you, I promise. So, long story short, how do you change the focal point of a lens or a mirror? What do? Go buy a new one. Understand that? Good. It's inherent. It's inherent in its radius of curvature. The radius of curvature tells you how much you're going to focus the light. Got it? Good. All right. Back to this. So, which is the first harmonic? The pinky, the blue, or the greeny? Well, it depends what the hell we got down here. What if I have time here? Time is period, right? Time it takes. So time as in period is proportional to wavelength, which is inversely related to frequency, right? Because period is 1 over frequency and wavelength is inversely related to frequency. You should be comfortable with this. Amplitude's completely independent. You have two waves that have different, the amplitude's completely independent of velocity, frequency, and wavelength, period. The amplitude has nothing to do with it. You have two waves, completely independent. Okay, so I hope you guys said that the pink was the first harmonic because it's the longest period or longest wavelength. The longest, please know the definition of fundamental, principal, primary. The first harmonic is the longest wavelength that can fit in a pipe. First harmonic. Okay, that's the first harmonic. Second harmonic would be the blue, and then this would be the green. Now listen, the general formula, if you get confused, 2L over N is almost always right. Like when you have sloshing water, woozy, that's 2L over N. When you have, remember good old Lake Michigan with its seeks and these little mini tidal waves, that's woozy, it's 2L over N. If you have a jump rope and you're playing jump rope, woozy. If you have a motorboat's creating a wave and a wake, that's 2L over N. Everything's 2L over N except when it's not. They're pretty, a test tube is one of the only ones that's like 4L over N. Clear? So 4L over N is like a test tube, or let's say open at one end. But if you get confused, it's always 2L, or some, there's some instruments that can be 4L over N, like a sax can be, and these kind of things, oboe. All right, wavelength is 2L over N. Well, this is a must-see TV. You ready? As harmonic increases, wavelength decreases. So the higher the harmonic, the third harmonic is going to have a lower wavelength than the second. As harmonic increases, wavelength increases, frequency increases, therefore period decreases. You gotta know this, guys. This is like the Mac Daddy of any lesson for waves. As harmonic increases, it's got a smaller wavelength, a higher frequency, lower period. So the lowest harmonic has the highest wavelength, lowest frequency, and highest period. Everybody understand this? You got to get this in your brain, guys. The lowest harmonic is the highest wavelength, lowest frequency, highest period. Please, please, this is just muy importante. They've had this passage on this test numerous times. Okay, the last thing I want to teach you guys is what constructive and destructive interference is. He sees me, I'm down. So for a wave to be completely out of phase, oh, how many degrees is a wave, by the way? 360, right? A wavelength is the distance it takes for a repeatable unit. You should really know that. So if a wave is 360, how many degrees to be completely out of phase would a new wave be? 180, 180, 180. No, 90's here. 90 wouldn't cut it. You got to be 180. When you're 180, every time you go down, I'm going up. And every time you come up, I'm going down. Everybody understand this? Yeah, it's pi. 2 pi for the unit circle is equal to 180 degrees, right? When 2 pi r, if r is 1. So yeah, it's pi. This would be a pi shift. Got it? Danny, you have no idea. I've got that stuck in my head for many, many years for very different reasons. Danny says she's got it now that I'm up, he sees me, I'm down, is stuck in her head. That's from freaking boot camp a gazillion years ago. They say when you're getting shot at, you're supposed to shoot. In boot camp, they drill us in your head and they say, shoot. And they say, I'm up, he sees me, I'm down, and jump down, and you'll never get shot. It doesn't work so well, I promise. But that's where that comes from. So yeah, I got that stuck in my head too, unfortunately, for better or worse. Okay, so back to work. Point is this. If we are 180 degrees apart, what happens is we will possibly complete destruct each other. Got it? So we will possibly completely destruct each other if our amplitudes are equal and opposite. So if our amplitudes are equal and opposite, when you add these two waves, you get flat line. Everybody feeling it? So long story short, complete destructive interference occurs when waves are 180 degrees out of phase and when they are equal and opposite in amplitudes. If you're not equal and opposite in amplitudes, you're going to get something in between. I'll get a little, so if this guy's way up here, I'll get a little hump when I add the two. Got it? So that they would end up like this. Everybody feeling that? Or like that, I should say. So that's when you get, now what is complete constructive? Complete constructive means we just add them. So whatever it is, so if we're complete constructive, and this is what I was talking about a minute ago. Look at this. Which wave has a greater frequency, the greenie or the red? Which wave has a greater frequency, the greenie or the red? They're the same. They're the same. Which one has a greater wavelength? Wavelength is the distance from here to here when I start again. They're the same. But what's different? So, Miss Elena, this should prove beyond a shadow of a doubt that my amplitude is completely separate from wavelength and frequency. Because these two waves have exactly the same frequency, exactly the same wavelength, but sure as hell that greenie's got a big-ass amplitude. Greenie's got a big old amplitude, oh yeah. Amplitude is intensity, it's proportional to intensity, it's not the same. So now, look at this. This symbol, folks, when this would be complete, what's that called? Complete constructive. Yeah, this is pretty intuitive, but if you've never seen it, you've never seen it. And this means 0 degrees or 360 degrees, which is the same thing. We're in phase. So, oh yeah, it would be louder if it was a wave, sure. Now listen. So it's just simple. If that's a 5 and that's a 15, then when you add these two together, you just get a new wave here at 20, but they're going to be in the exact same phase. Get it? Ooh, that's good. That's good. Clear? So when you add waves, if they're constructive, you add them. If they're destructive, you subtract them. Pretty much. All right. Good physics night. That wasn't terrible. Folks, enjoy your beautiful day. And I'll see you guys on Monday again. I promise I'll see you all again soon. So excited. Get some good work done. Get some heavy questions done. And I will see everybody soon. You guys are awesome. See you, Greg and Emery. What's up? Sarah, what's happening? Julia, my Julia. Sammy, what's up? Sunday won't be the same. I agree, Jake. I agree. I'm building something on Sunday. See you, Jim. Peace. Name is Danielle. Good night, Yorick. I'm glad you got the book. Damn. Final. It is happening to me. For a sound wave propagating through two solids of different density, the one will go faster. Hang on. Take care, Alexis. Faster through the more dense medium solid. Right. Correct, Max. That's not always true, Max, but mostly always true. Because it depends on other things, elastile strength. But the bottom line is this: if you're more dense, you have more particles to hit. So yes, for this test, you will put that as the answer. Clear? Rudy. You're welcome. Good night, everybody. Is a pi shift and a 2 pi shift both destructive? No. Sure. Why not, Zach? If you're 90 degrees, every time you're going up together, you're constructed. And if you look at the slopes, Zach. Don't look at the slopes. So if the slopes are going opposite each other, it's constructed. Clear? So it doesn't have to just be 0, 180, or 360 for sure. Does that make total sense? Good. Elena, what the hell did you just ask? Where was it? Yeah, no, if you're a 2 pi shift, then you're 180. I'm sorry, if you're 2 pi shift, you're 360 and you're in phase. So how can that? No, that's constructive, period, exclamation point. Got it? All right, everybody. Have a beautiful, splendid night. You've been a captive audience. I love you guys. Peace for all.
Elena, come and eat dinner.